Let's now consider the reactions of the 1,3,5-hexatriene. And let's take reaction with bromine in dichloromethane as an example. Bromine is the electrophile. It will be attacked by the pi bond. And it will be attacked at the end, because by attacking at the end, we generate a carbocation. And you'll notice that I've drawn this as an isolated carbocation rather than as a bromonium ion. The bromonium ion is a likely intermediate, but it would be very short-lived. Because unlike the other systems, this carbocation is stabilized by resonance. And we can in fact draw 3 resonance structures. With positive charge distributing on every other carbon. So we have the carbon on carbon 2 here. And here we have it on C4. And here we have it on C6. Where carbon 1 is the carbon that the bromine is attached to, because now that the bromine is attached, it takes the priority. In theory, any of these 3 carbocations can react now with bromide. And we should be able to get, as product, the 1,2 addition product, or the 1,4 addition product, attacks on the end, we should be able to get a 1,6 addition product. You'll notice that this system here, this allylic system, is actually a 5 pi electron system. A 5 pi orbital, I should say. 4 pi electrons, because the carbocation has no electrons on it. And we refer to that as either an extended pi system or a conjugated pi system. And we can draw the orbital energy diagram and sketch the orbitals for that 5 pi orbital system, which we will review shortly. For now, we want to consider the likely ratio of products. The 1,6 addition product has an internal diene, which is therefore the most stable product. So if this reaction is run under thermodynamic control, we would expect to get the thermodynamic product, which is the 1,6 addition product. The carbocation character is likely similar at carbon 2 as it is at carbon 4, because both of those are secondary carbons. But you'll notice that this no longer has a conjugated system. This has 2 isolated pi bonds. That's significantly less stable than either the terminal diene or the internal diene. So we would expect the 1,2 addition product to be the kinetic product and be the major product under kinetic control. And typically, that means low temperature, and thermodynamic control means higher temperature. So we would expect to get a mixture of 1,2, 1,4, and 1,6 addition products, but only traces of the 1,4 addition product that no longer has the conjugated pi system. The more stable internal diene will cause that product to be the thermodynamic product. The larger partial positive charge in the secondary carbon rather than the primary, and maintaining a conjugated diene in the product will cause the 1,2 addition product to be the kinetic product. So now let's take a look at what the orbitals look like for this 5 pi orbital conjugated system, or this extended alloic system. You'll notice that the odd numbered systems are not neutral unless they're radical, right? We don't have a ability to make a 5 pi electron system that is both neutral and has field octets on every atom. If we have a field octet on every atom, then it would be an anion. And if we have a neutral species, then it would be the radical. So what we want to look at is the orbital energy diagram for this 5 pi electron system. And the fact that there's a CH2Br here on the end is largely irrelevant. It would be identical if we were just looking at the pentadienyl system. Since it's an odd number, we know that there will be nodes that go through nuclei. So we can certainly draw the lowest energy orbital, pi1. We know it will have 0 nodes, and we know that the reason it's the most stable orbital is it allows the electrons to display or to spread out over all 5 nuclei. It should be more symmetrical than that. And it has bonding interactions with respect to all 4 carbon-carbon bonds, or 4 net bonding interactions. You'll notice I'm ignoring the CH2Br because that's not part of the pi system. Pi2 is going to have a single node. And because this has an odd number of carbons, that single node will be right through the center carbon. So the orbital on the PZ orbital on carbon 3 will have, or at carbon 4, if we're numbering it, this being carbon 1, will have no contribution to make to pi 2. It has two net bonding interactions. There is actually no interaction between carbon 2 and carbon 4. They're too far apart. They're separated by carbon 3, and carbon 3 has a coefficient of 0 on its p orbital. So there are two net bonding interactions. You can only have a bonding interaction or an anti-bonding interaction between adjacent carbons. If the carbons are not adjacent, then those orbitals are not going to interact or overlap at all. Pi 3 would be expected to have two nodes, and those nodes will be through the two carbons in the middle of the system. And you'll notice that this has 0 net bonding or anti-bonding. It has 0 bonding or anti-bonding interactions because the coefficient on those two carbons, carbon 3 and 5, by our numbering system here, or carbon 2 and 4, if we're considering just the 5 pi system, don't contribute, which means that there are only contributions from the pi orbitals on every other carbon. Because there are no net bonding or anti-bonding interactions, this will be a non-bonding orbital. And will actually have the same energy as the original p orbital energy levels. So if I wanted to put this on an energy diagram, and I start with my 5 p orbitals, since it's carbocation, I just have 4 electrons in those 5 p orbitals. Pi 3 is right here at the original orbital energy level, and then we have pi 2 and pi 1 in the bonding domain. Those will be filled with 4 electrons, so we have a bond order of 2. Our HOMO, in this case, is pi 2. Our LUMO is pi 3, and this is the reactive orbital for a carbocation. Because that's the orbital that a nucleophile will put electrons into, and it's a carbocationic species, so it reacts to nucleophiles at the LUMO. Notice that pi 3 has no electron density on carbon 3 or carbon 5, which is consistent with the fact that the products we got were 1,2, 1,4, and 1,6 addition, and never 1,3 or 1,5 addition. You can't put electrons onto this carbon. Bromine cannot react with either of those two carbons because there's no orbital present on those. Pi 4 we know will be anti-bonding. We know it'll have 3 nodes. And in fact, we know that it should have 2 net anti-bonding interactions. Because we know that pi 4 star should be the same distance above the original p orbital energy level as pi 2 bonding is below. And we know that pi 5 star should be the same distance above the p orbital energy level as pi 1 was below. And in fact, we know also that pi 5 star will have 4 nodes, and we know it will have 4 net anti-bonding interactions. So pi 4 star will have this node down through the center, but it will now have additional nodes between carbons 2 and 3 and between carbons 5 and 6. So there's an antibody interaction there, no interaction here because of the separation of the carbon that has no coefficient, and then an antibody interaction there. And the last orbital will have nodes between every set of adjacent carbons, 4 carbon-carbon bonds needing 4 nodes, 4 antibonding orbitals. Really, the only 2 orbitals we care about, though, are these 2. Because those are the frontier orbitals. And since this is a carbocation, the orbital we really need to worry about is the middle orbital, the non-bonding orbital. Putting electrons into that doesn't change the stability of the system. The stability of the system is controlled by this low energy pi1. And that leads to a slightly counterintuitive argument where the extended pi system, the 1,3,5 hexatriene, is simultaneously more stable than the 1,3-butadiene, the 4 pi electron system, and more reactive. It's more stable because the lowest energy pi orbital has a larger number of bonding interactions and is therefore able to spread its electrons out over a longer system and over more nuclei, which it wants to do. But it's more reactive because the reactive orbital, the HOMO, is closer to the original p orbital energy. So while pi1 goes down in energy every time we extend the system by an additional carbon atom, the frontier orbitals actually get closer, right? So the LUMO actually gets dropped closer to the middle, and the HOMO gets raised closer to the middle. So what I want to do next is I want to show you on the same scale the energy diagram for the 2, 3, 4, 5, and 6 pi electron system, and to think about how that causes the stability of the system to increase as the system extends in number, but the reactivity also increases as the system extends. And we'll also tie that to the ultraviolet spectroscopy, because these extended pi systems, actually any pi systems, have orbitals that have an energy gap, delta E, that corresponds to a frequency in the ultraviolet range. So we can use the ultraviolet absorption, the actual wavelength, right? Because the wavelength is inversely proportional, so delta T is also equal to hc over lambda. We can use the wavelength of the absorbed ultraviolet light as a measure of the extent of the conjugation of the system. We'll talk about that in the next video.